Today I'm going to talk about Define, an interactive control plane software debugger that can be used to debug the bugs and defects that you observed in the production network. It can also be able to help operators analyze bugs that are reported by automatic debugging tools. So by using a deterministic execution, our tools can scale to large-scale networks without using comprehensive logs. So this work is a joint work with Virajith and Professor Matthew Caesar and Professor Jacobus from Merwe. So control plane software lies in the core of large-scale networks such as data centers, enterprise networks, and the campus networks. The purpose of using control plane software is to draw a network map and to direct data flows from their sources to their destinations. To be able to operate in a complicated environment and to handle different kind of bugs and defects, this kind of control plane software is implemented really complicated routing protocols. Due to the complicated implementation, recent studies have shown that control plane traffic is responsible for 95 to 99% of the bugs that we see in today's network. So to address these bugs, operators first try to use automatic control plane debugging tools. So automatic control plane debugging, most of these techniques tries to build a model of the software itself or the observed bug in the production networks. What they do is either statically analyze the source code or try to dynamically analyze the software behavior. Unfortunately, when this kind of automatic debugging tools works on control plane softwares, most of them just detect the anomalies instead of show the operators how to correct these bugs. For instance, tools will tell operators that when you set up your control plane software in this way, you will see loops in your networks, or you will see black holes in your networks. But there's no way yet for these tools to tell operators how to fix those bugs. So eventually, the operators have to go inside the network and run the control plane software again to actually understand the bugs and find the solutions themselves. So in today's networks, operators has a little choice but to enable logs on network nodes to be able to really understand what's happening inside of your networks. So all this, the reasoning to turn on the logs is to record the non-deterministic events that we cannot reproduce precisely inside the debugging network otherwise. So there are two approaches to use logs in today's networks. The first one is to use comprehensive logging, which we enable logs on every single network node inside the network and record every single non-deterministic event. So the result is that we will be able to reproduce the precise software behavior in the debugging network. However, the large amount of logs makes the human operator unable to efficiently manually observe the bugs with these logs. Even when using automatic tools to analyze these logs, the size really affects the effort and time spending on debugging. Even the researchers that developed these automatic tools have mentioned that it is impossible to use a comprehensive logging in production networks, in today's production networks. So the common practice now is to enable partial logging. That is, instead of logging at every single network node, we pick some critical network points to enable the log. The way we pick the places to log the network events today is by using using experience. And instead of logging every single non-deterministic event, we log important events that we deemed necessary. The reason to use partial logging is that by doing so, we can be, this techniques can be able to scale to large-scale networks today. However, like we said, everything that we log and every places that we log is by experience. So if we see some new bugs or some bugs that we are not expected, we will not be able to precisely reproduce them in the debugging network. In our paper, we demonstrate 2 real-world examples in today's popular routing softwares. And we can see that partial logging is unable to precisely reproduce these bugs. So today, I'm going to present Define. And our goal is to address this problem. We would like to precisely reproduce the bugs that we see in the production network. We wanted to do so while maintaining the efficiency inside the production network. We would also like to provide interactive control in the debugging network for the operators to understand the bugs and defects they observed. Finally, we would like to be able to overcome the limitation of using comprehensive logs. We would like to precisely reproduce every bug that we see in the production network while be able to scale to enterprise and campus networks. So to do so, instead of using comprehensive logging, we try to use deterministic execution to manipulate non-deterministic events. So recent studies have classified non-deterministic events into external non-deterministic events and internal non-deterministic events. External non-deterministic events means the events that is not controlled by the control plane software itself. This includes routers or link goes down or up. And internal events includes that the events that we can, this networks, the control plane software can control and manipulate. So to handle external events, because the control plane software cannot manipulate them, the only thing that we can do is to log all these non-deterministic events. Fortunately, these events is not that, the amount of these events is not large compared to internal events. For internal events, luckily, we can be able to manipulate their ordering and timing when to deliver them to the control plane softwares. So we designed our system to manipulate these internal events and eliminate the non-determinism. To do so, instead of running control plane software directly on the operating system, we implemented Define as a library that intercept and manipulate non-deterministic events before we deliver them to the control plane softwares. Define record external events using virtual times. In addition, it intercepts internal message events and manipulate them, order them, and send them to the control plane software in deterministic ordering and timing. Finally, we provide a set of deterministic timer APIs for the control plane software to use so that the result will be deterministic. We also wrap around some non-deterministic system codes so that the control plane software themselves can be running deterministic on a single network node. So to be able to provide efficient performance in the production network and be able to provide debugging interactive control inside the debugging network, what we do is that we introduce 2 different algorithms in different environments. In the production network, we use DefineRB to efficiently record the execution of the production network. We implement speculative execution, and whenever the events doesn't happen according to the designated ordering and timing, we roll back the states of the network software and replay it in the correct order. In the debugging network, we use DefineLS. Instead of go for efficiency, what we try to do here is to provide an interactive control for the human debugger. The human debugger can use DefineLS to step through the network with a lockstep algorithm and inspect the bugs and defects that it observed inside the production network. In the rest of the talk, I'm going to provide a high-level description of both algorithms. Then I'm going to provide evaluations for the performance and the scalability of both. Then I'll wrap up the talk with the conclusion. So inside the debugging network, what we try to achieve is to preserve the convergence time of the control plane softwares. What matters the most for control plane software in the production network is that whenever a link goes down or goes up, the message has to be quickly broadcast into the rest of the network nodes. Because most of this information update is broadcast, using a stop and wait algorithm is not efficient. So in our design, we instead using a speculative execution. That is, for each single network node, we record the history of the non-deterministic events that the network node receives. Whenever a new non-deterministic event happens, we use ordering function that is independently determined by each network node to order the list of non-deterministic events. If the events comes in the correct order, we deliver the events to the control plane software and to process them. If the control plane if the events comes in the wrong order, we roll back the state of the single network node and replay the events in the correct order. So in the next few slides, I'm going to talk about how do we roll back the network state of the softwares. And then I'm going to talk about how do we come up with an optimized ordering function. So to be able to roll back control plane software states, we use a modified fork system call. So when a single control plane software started, DefineRB instruct the control plane software to make a fork code to preserve the state of the control plane software itself. We modify the fork code so that non-deterministic data such as PID and open files are preserved across the different processes. The parent process is used to maintain the states that we want to preserve. And the child process is going to carry on the execution. We establish a shared memory between the child process and the parent process to communicate the information when the rollback is needed. Then DefineRB will use the child process to continue on the future non-deterministic events. Whenever a non-deterministic event comes in the correct order, DefineRB let the child process the events itself. Then it uses the fork system call again to preserve the states after we process the non-deterministic events, and use the new child to continue on process the future non-deterministic events. So whenever the non-deterministic events comes in the wrong order, what we do here is that we DefineRB instruct the child process to exit and use the shared memory to tell its parent the correct PID it needs to roll back to and the list of messages that it needs to play back. When the parent process resumes execution, it reads from the shared memory and to see if it is the final process that should exist. If not, it will continue to roll back. So when we roll back to the final state, the DefineRB library will instruct the control plane software to replay all the messages in the correct order and reconstruct the process chain. So this process allows us to make the execution deterministic in the production network. So because of the rolling back is not a lightweight process, what we try to do here is to limit the number of rollbacks inside our network. The first thing that we do is to introduce a logical timestamp. We use a leader election algorithm to select a node that will periodically send out logical timestamp. Whenever a node receives this timestamp, it will tag external events with this timestamp. It will also tag the broadcast messages associated with the external events with the same virtual timestamp. it will also try to fire timers in logical time instead of in physical time. Doing so allows us to properly record external events and properly replay them. It also allows us to simply deterministically manipulate the timers. However, when we are dealing with internal broadcast messages, cascading rollback may appear because whenever two messages occur within a single logical timestamp, we have to order them in some way. If we cannot handle them correctly, then the cascading rollback will happen, as in this example. So in this example, we show that in a network, when inside a single logical timestamp, if we have two broadcasts happen at the same time, and if we come up with a random ordering to order one broadcast over the other, what will happen is that we will have a lot of rollbacks inside our network. So the broadcast will proceed as follows. When each network receives the broadcast, it will send it to its downstream routers. So if a router receives the packet in the correct order, it will do nothing but send the non-deterministic message to the ControlPlane softwares. But if the router receives the packet in the wrong order, it has to roll back the state of the softwares. So unfortunately, when the ControlPlane softwares process the a message in a new ordering, it might generate different output when doing so. So in this case, this router might want to retract the rate messages that it already sent it to its downward streams. So it has to send messages to tell the downward stream that it doesn't want the original read messages to be processed. Unfortunately, because we use speculative execution, the message is already sent downward streams. So in the worst case, we have to roll back almost all the network. We have to perform rollbacks on almost all the network nodes. This is a heavy-weighted this is a heavyweight process, and we want to avoid this whenever possible. So we address this by encoding our latency information inside the packet itself. What we do is that for each link in the network, before we start the ControlPlane softwares, we measure their expected latency. Because this latency are on the single link, and because the modern network ControlPlane softwares has its own high priority queue, this expected latency doesn't change a lot. So whenever two broadcasts happen inside a single virtual timestamp, we record the expected outgoing link delays onto the message. And whenever the message is broadcasting to the network, the expected delay experienced by the packet is accumulated on the given packet. When a network node receives two packets, it will compare the expected delay that these two packets experienced so far, and it will order them in the ascending order. Because we are using virtual time in the first place, so the broadcast happen in a single. If we speed up the rate of the broadcast virtual timestamp, we can make sure that the broadcast that happens inside the single timestamp happens really close together. And this makes our latency information valuable because we can reduce the amount of unnecessary rollbacks. As we will show you in the evaluation, that this optimized ordering really helps our performance inside the production network. So after seeing how we deal with deterministic execution in the production network, we show you how do we reproduce the execution inside the debugging network. So inside the debugging network, our goal is not to perform deterministic execution efficiently. What we try to do here is to provide a developer a way to inspect the bugs and defects in detail. So what we do here is that instead of using a speculative execution, we use a lockstep algorithm by dividing the execution into logical steps. For each step, we execute each step in two phases, the transmission phase and the processing phase. In the transmission phase, we make each network node send messages and receive messages from its neighboring nodes. And in the processing phase, they process the nodes and get out the results. So let me give you an example of how do we use how DefineLS works. So DefineLS uses two message queues, one receiving queue and one outgoing queue for each control plane softwares. When receiving the messages, when receiving the message in transmission phase, DefineLS doesn't send this message to the control plane software yet. It puts them in the queue and order them with the same functions that they use in the production network. In the processing phase, these messages are delivered to the control plane softwares and put in the outgoing queue. And inside and then when we go to the next transmission phase, this message is delivered to the neighboring nodes. By doing so, we will be able to precisely reproduce all the message ordering inside the production network. To be able to step through this message transition phases, we use a centralized coordinator to allow developers issue step commands. The step can be set up in different granularities. For instance, we can do it per events or per logical time units. I'm going to present evaluations on these two algorithms. I'm going to first present the performance evaluations and then the scalability evaluations. We perform our evaluations on the popular control plane platform XORP using the OSPF module. We perform our evaluation on EmuLab, and to be able to reflect the real-world scenario, we use the Rocketfuel topology. To be able to analyze the scalability, we use the bright topology generators. We use traces from Tier 1 ISPs of 2 weeks. So I'm first going to show you the result of DefineRB. So as you can see, we plot the convergence time into the CDF form. So in this figure, you can see that the convergence, 99% of the convergence time is comparable to the vanilla XORP. So the 1% of the time is that when the cascading rollback occurs. So DefineLS, to evaluate the performance of DefineLS, we measure the time of each single step commands consumes, and we plot the CDF figures as this. So as you can see that every step commands will respond in less than 1 second. We do the same experiments for scalability. For DefineRB, we measure the convergence time for different number of nodes. The red line represents the vanilla XORP, the performance of the vanilla XORP, and the green line represents the DefineRB performance using the optimized ordering. The blue line represented the DefineRB, but using it without the latency information. As we can see, although in this figure we plot the average and as well as the standard deviation. As you can see that although the average, the difference of average increases between the DefineRB performance and the XORP performance, the fact is that for most of the convergence time, this doesn't the performance of DefineRB is comparable to to XORP. However, it is just 1 or 2 long cascading codes that affect the average that we see here. But we can see very clear from the figure that when we use optimized ordering, it can really reduce the amount of performance, the amount of time we used in the network itself. It can also, the actual difference between the DefineRB and XORP isn't that huge. We also performed the scalability evaluation for the DefineLS experiments. And we can see that all the timestamp, the average of the timestamp is less than 0.8 seconds. So in this talk, we present an interactive debugger for ControlPlane software that complements the automatic debugging techniques. By using deterministic execution, we can avoid using comprehensive log, but we can still precisely reproduce the software's behaviors. We used speculative execution to maintain the performance in the production network and lockstep algorithms to provide interactive control in the debugging network. And thank you. This is my talk, and I'll be happy to take questions.
Question for you. John Howell, Microsoft Research. And so my question is, your rollback case, in the common case, every time you receive a non-deterministic message in the production system, you fork. And that sounds like it might be really memory intensive. Do those chains get really long, or is the common case that they actually stay short and so you're not actually soaking up a bunch of memory?
Right. So that's a very good question. Actually, we maintain because we use fork in different timestamp, we actually maintain only a deterministic amount of timestamp of forks. So in addition, because we use fork, actually the physical memory is shared by a lot of processes.
Sure.
So yeah, actually when we measure the physical memory usage, they are not actually that. It's only 2% overhead compared to vanilla XORP, right?
And so how long do those chains get?
Actually, it's not a lot because it only happens when external events happens. So yes. Otherwise, otherwise the message is not broadcast. So not a lot of network node needs to fork for the events, right?
Thank you.
Okay, thanks.
Do you have any other questions?
Great, thanks.
All right. Thank you very much.